Now we have Kaya Sorli from the Laboratory for Atmospheric and Space Physics at University of Colorado with a 3D model, thermophysical model for binary asteroids. So trying to make sense of all of this, I suppose. Take it away.
All right, thank you very much. So my name is Kaya Sorli, and I am working with Dr. Paul Hain here at the Laboratory for Atmospheric and Space Physics. And today I'd like to talk to you about our efforts to develop a three-dimensional thermophysical model for binary asteroid systems, the results of which are immediately applicable to multiple upcoming missions and to broader questions about binaries as a whole. This work is supported by the NSF as well as by NASA's Janus mission. Okay. So binary asteroids inhabit a particularly intriguing blind spot, I'm going to take that mask off, within the planetary catalog. And that's because they are strikingly common, if this decides to move forward. Yeah. About 15 to 16% of near-Earth asteroids are believed to be binaries. And within that, we also find them in all major asteroid groups, with some evidence even suggesting that in places like the Kuiper Belt, they might be more like 50% of the population. They're also strikingly diverse, showing a diverse range of spectral types, sizes, and orbital dynamics. But we're pretty sure that most of them are rubble piles with small secondaries. However, within that, they also are, well, this is not, sorry. No, you're good. They also demonstrate quite the range of unique evolutionary and dynamical pathways, which means they can inhabit very different end states. For instance, you can end up with a stable, tidally locked system, like the system 1996 FG3 shown at top here. That's one of the Janus targets, as well as chaotic systems like 1991 VH shown on the bottom. You can, however, also end up with contact binaries like Itokawa, or break the binary apart entirely. But there's a lot of open questions here, because we currently lack high-resolution data on binaries. We haven't actually visited one of these in situ. So we don't have visual data, we don't have IR data. But that's about to change, because these unique properties have made binaries the target of several upcoming missions, most notably the DART, Hera, and Janus missions. As many of you are probably familiar, DART is the first planetary defense mission, which will test a technique known as kinetic impact by impacting the binary system Didymos. A couple years later, Hera will follow up on that, using IR imagers and other instruments to look at internal properties and also the legacy of the DART impact. As I mentioned, though, I'm doing this work for Janus. So for those who might not be familiar, Janus is an upcoming NASA Simplex mission, which will send dual spacecraft to two different binary systems, the stable 1996 FG3 system and the unsettled 1991 VH system. Each Janus spacecraft will carry a visible and infrared imager. As some of you may have also heard, Janus is a rideshare with Psyche. Psyche has been delayed. At this point, our spacecraft are nearly complete, and we are still a rideshare on the Psyche mission. We still have that. And we will be waiting, and we're waiting for further direction from NASA at this point before we proceed with next steps. Thank you. So where does thermophysical modeling fit into this? The answer is that it's critical for both mission interpretation and for looking at binaries as an object. So in order to interpret mission data from infrared cameras like those on Janus or Hera, you need to compare it against model outputs. And that can tell us information, as we've seen already, about surface properties. For example, are we looking at bare rock or porous regolith? And it can also teach us about things like their thermal properties, so thermal inertia is kind of notable there. But it can also teach us about their evolution. Thermal effects can dramatically alter binary systems, and the most notable of these is the binary Yorp or Bjorp effect. So to kind of explain what that is, for a single body, if you have, like this shown on the right, if you have asymmetries in shape, the fluxes that are absorbed will re-radiate in an asymmetric way. As a result, you'll end up with a torque on the object that can change its orbit. This is known as the Yorp effect. If you then move that asymmetry away, like a secondary, then you end up with a torque on the secondary, and that can change binary orbits. It can spin them up, spin them down, make them a contact binary, or break them apart entirely. So understanding BORP is critical to understanding these objects. Additionally, BORP can potentially be used, since those torques dissipate in the interior, to understand a little bit more about these asteroid interiors. To understand how big this effect is, we need thermophysical models that can give us accurate temperatures and how they change with time and with shape. So that's where we step in. We're working on developing an advanced three-dimensional thermophysical model that can be broadly applicable to any binary asteroid system. All right. Thank you. So what makes this complicated? So in addition to the fact that in a single body, you have to take into account the fact that incoming solar radiation will be reflected, there will be shadows, and also it will re-radiate out in a different direction than it was absorbed due to orbits, you now also have two bodies. So you have to think about primary-secondary radiation exchange in the form of infrared scattering or reflection. But you also have to think about the lack thereof, like eclipses. And the only way to do this is with three-dimensional modeling. So we started off with a single body 3D model that we did at a high level by coupling the highly validated 1D thermophysical model from Hain et al. 2017 to 3D shape models produced by the Janus team. By feeding in parameters and calculating fluxes like those shown on the bottom left, we can get diurnal temperatures for each facet like these shown on the right. These are both for the 1996 primary, FG3 primary. We have previously modeled all 4 Janus target bodies, and for anyone who might be more interested in those specifically, I would recommend checking out my LPSC poster from this year. So, as I mentioned though, binaries are strange. And there's a lot of things we need to take into account here, like eclipses and shadowing. How do we do that? How do we take into account light in a system? And the answer is something called ray tracing. So the model as we've developed it, thank you, takes in 2+ shape models and includes ray tracing, which essentially traces the path of light and fluxes throughout a system. That allows us to do things like calculate view factors, which tells us what facets can see other facets, which helps us calculate reflection and scattering. We also use an efficient KD tree structure that divides the space into a k-dimensional space, and that actually allows us to cast way fewer rays, making it more computationally efficient.
3 minutes.
Also calculate temperatures by balancing direct insolation, infrared emission, visible light reflection, scattered IR radiation, and 1D heat conduction. And we track shadows and eclipses like shown here on the right. Can we skip? Thank you. So here's a preliminary model run with that. Using, for the 1996 FG3 stable primary, we use a thermal inertia of 120 SI units like that from Walters et al. 2011. We get a diurnal amplitude of the equator of about 105 K and a global range of about 90 to 310 K. We also get a thermal, for the secondary, use a Bennu-like thermal inertia of about 310. We get an equatorial diurnal amplitude of about 75 K and global range of about 90 to 300 K. As you might have noticed, this is only one thermal inertia value for each of these. So future model runs are going to scan over pertinent parameters, notably thermal inertia, so we can get a holistic view of these systems because that's necessary for BORP. Can we skip forward? Awesome. Thank you. And so, in conclusion, we have developed an advanced three-dimensional thermophysical model for binary asteroids. And I want to emphasize that this model can be used on any binary or solitary asteroid, including non-Janus targets. So, and that allows us to interpret and constrain against observational data, like that what we'll get from IR imagers on Janus. And it will also eventually help us calculate the magnitude of this BORP effect in these systems, which is critical for understanding their evolution. We also completed an initial temperature model of the stable 1996 FG3 system, and an upcoming publication for later this year will scan over pertinent parameters to get a holistic view of these systems that we can then use later. Thank you very much.
So we have a question from online that says, why Bennu like TI when Bennu is a B type and not an S type?
So it's a good question. We're kind of operating right now on the fact that we had primary data and we don't have it for the secondary. So we're kind of going off of the rubble pile assumption. And as I also mentioned, we're going to scan over a lot more values for this. But it's a very good question, and it's definitely one that we're going to have to consider in terms of types and what data is available.